exercise. I'll do that now.
Yes.
I swore I did first. I was just thinking about that. Yes, we are. Thank you very much.
No problem. Let me know if you need anything.
Thank you. Hello, you're from C++.
Yes.
Please join us, grab a seat.
You have an extra seat because I'm waiting for my event. They start at 8 o'clock. Only if you have place.
Yeah, we have. Hello.
You've moved places, you're confusing me.
Yeah.
I have to start assigned seats like in the classroom.
Yeah, everybody gets the same.
Yeah.
Okay, welcome everybody on the 24th class C++. We're almost at the end of this course. There is one extra class and then we're restarting, as you know, on the 1st of May. Today is, am I correct, revision, yes?
No.
Oh, perfect. So perfect forwarding. Sorry.
Semantics mostly.
Yes.
A little bit about perfect
Sorry
forwarding.
about that. Yes, that's true.
Hey.
So we will be starting this. Now, as you know, we're obviously trying to improve our website. We had some reports that the website opens quite slowly and renders not very well on
Mobile.
Chrome
Yeah.
and so on. So we're working on that.
The fancy video in the background is very nice, but maybe kills your mobile.
Yeah, I think that is the problem.
With C++
I'm not
programmers, not web.
Yes. I'm not being the fancy guy here. My quality control and visual things may not be the best thing to judge. So I'm not. I will leave this to the betters. Now, what else? Very important. Well, not very important. Just as a kind request. If you try to eat the food before, because that obviously gets trouble for people, yes, especially for teachers when they're sitting with rumbling belly and they're sitting looking at the people eating. That's a challenge, and other students as well. So really kind request. If you feel very hungry, just pop out outside, come back, and then obviously off we go. Obviously, if the guys are telling something, it's over your head, you don't understand it, don't be afraid to ask. I do ask, but I don't want to be honest as the only person who does not understand something, because I feel like an idiot then. Yeah? So join me, help me. Without you, the guys will say, okay, they understand everything, I got a brilliant class. So if you don't ask questions, they assume you understand. If you don't, tough luck. So on that note, on that bombshell, I'm passing you to Tristan.
Okay. Good evening. Hi. Yes, new face, which is lovely. Welcome, even if you are only here temporarily. Okay, well, everyone else has seen this, but you haven't. But if you want to, we have this Slack channel. You can come and talk to us. You can join us. We'd like to hear from you. The other thing is, as Tom said, we're restarting from scratch at the start of May, and we're going to have a more sort of well-defined lesson plan than we have had to date, where we've almost made it up as we've gone along. We've relied on feedback a lot to sort of decide what to teach, but we've come up with a pretty decent progressive lesson plan. But I guess we'll tell you probably more about that next week. Or
Yeah, we're thinking share the syllabus.
okay, well I don't have it now, so I can't do it right now.
I have.
We'll put it on the website anyway. Yeah. Okay, so today we're going to talk about move semantics, perfect forwarding, all that stuff that was added to C++ 11 that people find very confusing. Some of it because it is quite confusing. I have to be honest, this is not an introductory level talk. Right, this when we rejig our things, this will be in the advanced part of the course. So if today is your first day doing C++, this might be a bit tricky. But anyway, yes, so we're going to talk a little bit about motivation, why this nasty complicated stuff was added. We're going to talk about expression value categories, we're going to talk about R-value references and standard move. move constructors, move assignment operators, and then a bit about universal references, forwarding references, and standard forward. At this point, there's a confession, a mea culpa. I intended to give you a nice exercise at the end, but I just ran out of time to prepare it. So it's basically going to be a lot of me talking. So sorry about that. Usually we try to balance out the sort of lectury parts with some actual hands-on coding, but I just ran out of time this week, so sorry about that, guys. Anyway, does that all sound good? Particularly to Joshua, who asked for this class, so it's all for you.
Thank you.
Okay. Whoops. Back up. Right. So why? There are two things that all this horrible move semantics stuff was intended to solve, and the first is efficiently stealing the contents of another container. So So with a vector, for example, if you know its life is going to end, and you want to transfer it somewhere else, in C++ 98, the only way to do that, well, not quite, but almost the only way to do that, was by copying the container. Right, and that's an expensive thing to do. You have to allocate a new memory area. You have to sometimes copy each individual element over, which could be millions of them. And it's much more efficient if we could just take the guts of the vector and move it into a new vector elsewhere. So we want to be able to steal, sorry, yes?
The problem you mentioned once, you can't return a reference to local variable.
No,
It's not related to that.
It's not related to returning a reference to a local variable, no. No, although, if you return a local variable by value, if you return an object from a function, so then you will get move semantics happening then. It will automatically move the variable out, it won't copy it, which is quite nice. And the other problem this was intended to solve was something called perfect forwarding, which is a bit more specialized, I guess. Sorry.
So does this work for base types?
Fundamental types are movable, yes, but their move operation is the same as copy. It's no more efficient. So for an int, you're just literally copying the bits from there to there. So you can't move an int as such. It doesn't do anything special. And as we're going to see, that's if you don't write a specialized move constructor, then it falls back to copy. But we'll talk quite a lot about that in a minute.
So is move basically just copying pointers?
Is it just copying pointers around? No, there's more. Well, there's more to it than that, because move semantics is what enables standard unique pointer to work. So before that, we had this awful thing called auto pointer, which tried to do this stuff but with copy constructors and was horrible and nightmare to use. And unique pointer, because it's a move only type, you can't copy it. It enforces some guarantees, which wasn't actually part of the original design, but sort of falls out as a nice byproduct of the move semantic machinery.
Can you make some example in which I would like to extend the lifetime of an object? Because reading like this, it sounds to me like bad programming. Because if something is inside a scope, I expect it to end with the scope. In which case, I might wish to prolong it and to bring it aside. And why don't I just plan and make it on the upper scope or something like that?
Okay, so let's think about a factory function that returns a vector. So you have a whole load of setup code that fills the vector with values, and then you want to return that somewhere else.
You mean a factory just of vectors?
Yes.
Okay.
So, your calling function says create vector, and that creates this vector filled with 1 billion values.
Yeah.
When we return that big vector from the function, we don't want to copy it. We don't want to copy it out of the function. We want to just be able to steal the guts of that vector.
Because even if I return, it will make it die and then copy it?
Yes.
Okay.
Well, in principle anyway. Compilers are pretty good at optimizing that, but we'll talk about that.
I was expecting this kind of optimization when you return a structure like that.
So, yes, we're mostly going to talk about this the move semantics and stealing, and we're going to really get into detail about value categories, which is the other thing that really confuses people. And then we'll talk about perfect forwarding, standard forward in the end. Okay. Oh, do you know what I forgot? I usually set my slides so they all reveal a little bit at a time. So I forgot to do that, so you're going to get ahead of me, but never mind. So the fundamental copy was a fundamental operation in C++ 98. So creating an object, copying an object, deleting an object, comparing the values. These are fundamentals of the value semantic system that C++ 98 has. And copy is still fundamental in modern C++ as well, but there's a new fundamental operation of move. So moving is similar to copying, except that it can potentially modify the thing that you're moving from, potentially. So you can sort of think of move as an optimization of copy, sort of, but that's, and I've stood here once and described it like that as a kind of throwaway, very basic introduction to why we do it, but it's actually a bit more fundamental than that. Better to think of it as a separate operation. However, if we do nothing special, if we don't define our own move operations, or the types, the contain types, if there's no special move operations on a tree, we'll fall back to copy, right? So every copy is a move operation, right? Because if you think about it, actually, the next slide's going to make this easier. We'll move on. So the idea of copying is that you create you assign an object the same value as a source object. Right, this is stuff from lesson 1, which was 6 months ago now, terrifyingly. Right, so we have two vectors here. First one contains these values 1, 2, 3, the second one is empty. And then we assign B to A. That's the wrong way around, isn't it? It should be B equals A.
Yeah.
Apologies. Yes, sorry. This will work.
That will make it a very nice empty vector.
Yeah, whatever. There we go. Just like I said all along, like it was right at the beginning. I'm going to have to make sure the next slide says the right thing. Just a second. Oh. Right. So just as it always was, albeit in the wrong font now, we've assigned the value 1, 2, 3 to the object B. So A and B now have the same value. They're not the same objects because we have value semantics in C++. So if you did this in Python or something, you'd get reference semantics, it'd be shallow copy. This is a deep copy in C++. This is value semantics. But crucially, this doesn't change A. All we've done is copy A. Moving, on the other hand, does change, potentially changes the source object. Okay? So now we have the same thing again, like it always was. And in this case, we are using this magic function standard move that we'll explain in a while to move the contents of A into B. And after this operation, B is guaranteed to contain 1, 2, 3. Sorry, I've got it the wrong way around again, haven't I? Whatever, you understand.
No?
The comment is contain 1, 2, 3.
B will contain 1, 2, 3, and A is in a moved from state. Yeah.
Obviously, the bullet point is wrong.
God, I really should have proofread these before I came here.
That usually happens to very good developers. So
Well.
we're fine.
Yeah, I mean, I don't even bother compiling my code, I just write it and see what works.
Tristan, can I give you just a suggestion? Just say that there are specially made mistakes for you to notice them.
Yeah. Yeah, prize, free cup of coffee to whoever notices.
Yes.
Free cup of coffee to whoever notices the mistakes. Right, so B contains 1, 2, 3, and A is in this undefined moved from state. So we don't know necessarily what we can do with A. We have to look at the documentation, but again, we'll talk about exactly what moved from means in a while.
So in this case, if we have on the next line saying A equals B,
Yeah, that would be okay.
that would be okay.
Yeah.
But if let's say you said A square bracket 0,
Yeah,
that might not be okay.
exactly. Precisely, very good explanation.
You're welcome.
Sorry, the pointers of B and A are different or not? Begin and end.
They're distinct objects, so they're, yes,
Yeah,
they're,
okay.
yeah. Yes. Now, interestingly, the data pointers, so if you did .data, now we might have moved the internal data, but then again we might not, because move is sort of a magic operation.
And if we can't move it, does it just still copy?
Yes. Exactly that. So we say potentially, moving potentially moves and modifies the source object, but it doesn't have to. So a copy still does the same thing, it still assigns the value, it just happens not to modify the source object. So any way you can do a move, you can do a copy. So rather than thinking of move as a more efficient copy, it's probably better to think of copy as a less efficient move. Yeah.
Can you do moves on constructors?
No.
You know me on what?
Construct.
So why do you think that is?
Because it changes, maybe changes the construct. You can't do it.
Exactly.
You can't combine it.
Yeah.
Physically, if you wanted to. If you made a class and you declared a constructor or move type operator that took a const and to your type, then you get a mutable field, you physically do it. You're pretty much violating what anyone's going to read.
You'd still need to const cast, which might be illegal.
Yeah, but mark it mutable, the field would be marked mutable.
That brings me to my next question. Can you have a const vector of a ampersand?
You can't have a vector of references. You can't have a vector of L value references, you can't have a vector of R value
No, what I
references.
mean is vector of int.
Yeah.
Const.
Can you have a const R value reference?
Yeah.
Yes, you can. You probably don't want one because they're not very useful. They can occur. When we get onto this a bit more, I might tell you exactly when they can occur, but they're not very useful because, as you said, you can't move from them. Any attempt to move from it will degenerate to a copy.
So two questions. 2 slides ago you were mentioning non-movable object. Non-movable means the one, so only const or other non-movable?
It just doesn't have a move constructor or move type operator.
Okay, just that. And same then for the copy work. We don't have a copy constructor.
Yes.
If it's not copyable, it won't have the const and.
Yeah. So all.
Sorry, the second question is when I then do a movie, what happens at work level? I take another chunk of memory and I copy my data, or this is what we want.
Depends on the type. So, do you want to tell him?
Oh, go ahead.
Alright. The std vector, right, internally inside that, because it's just a class, it's going to have a field that's pointed to some array assembly, right?
Mm-hmm.
So then it's got a constructor, it will have a constructor and an assignment operator overload for T and, where T is the std vector type, right? So there's T and, which is L value, and which is R value, which is what we're talking about here. So, say it's the constructor, right? It's saying I'm getting an R value reference, the and to the other one. And what std move actually does is it just says, consider this type to be type and instead of being just type and. So, inside the actual code of your constructor, you now know that you can receive an R value, so you can just say, well, my pointer equals that one's pointer, that one's pointer equals null pointer. So now I've got the pointer, because it's very cheap to do, copy the pointer, set that guy to null, return, we're done. So that's a very basic.
I'm going to show you an example of doing this in a while. Right. I'm now really nervous. I made loads of mistakes, by the way. Anyway. So we're going to talk a little bit, going to go quite in depth about value categories. It's not really essential to know about value categories, but you're all, well, almost all of you, have been here for several sessions, so I reckon you can probably handle it, but if there's anybody online who's tuning in for the first time, you don't really need to know all this in order to use move semantics, but I thought it might be interesting or not interesting, or, you know, I'm going to tell you anyway. You're all stuck here. Statements and expressions. Does everybody know what the difference is between a statement and expression? I think it's some programming language theory now.
The expression result in a value.
Yes. So statements are things like if and for and declarations and things like that. Expressions are things that have a value, that have a type, have a result. This is sort of not true because actually a C++ program only has statements in it, but if you put a semicolon after an expression, it turns it into a statement. So we have some examples of some expressions here. So just assuming we have int x up there somewhere, a declaration of a variable x, then the name x by itself is an expression. It's an identity expression. Just 42, or any literal, is an expression. X equals 3 is an assignment expression. If we put int at the front, then it would be a declaration, which is a statement. But if we just say x equals 3 for some already existing variable x, then that's an assignment expression. X plus y. This is the interesting one. A function call expression. So we call a function, we give it some arguments. That result of that function has a type, as we'll see, it has a value category. It's a function call expression. And then we have this horrible complicated thing at the bottom, which I was just put down to show you that expressions have sub-expressions. So this whole thing is an application of the ternary operator, but it's got several different sub-expressions. So each one of these, so x and 10 are expressions, the less than operator is a sub-expression, this is another sub-expression, etc. You can break it all down. So that's really, you know, if you're really fascinated in programming languages. But the takeaway from this is these things are expressions. Every expression has a type. Right? So, yes.
So if your function returns a void, is that still an expression?
Yes. It's an expression with type void. Every expression has a type. Right? So if we had up here, we had int x equals 0, then the type of x would be int. The type of 42 is int. The type of the assignment operator, well, it returns a reference to int, actually. Assuming x and y are ints, this thing's going to return you a new integer. We have no idea what the return type of foo is. It depends on the declaration. And I couldn't possibly tell you what the return type of that thing is, but the compiler can work it out, which is nice. Or if you can't work it out, it'll give you an error message.
Does that mean, after the question mark, the type of the two parts have to be the same?
They have to have a common type. The ternary operator is just mind-bendingly complicated, right? But it does have well-defined rules. So if there's some common base class that they can both be converted to, then it'll be that. But it also takes integer promotions into account. So if you give it a long and an int, the result will be a long. There are all sorts of rules to it.
Are you saying the y could not be a float and then the x and int?
Potentially.
That would work.
Potentially, yes.
But y couldn't be a vector and x couldn't be a map. Obviously not in your example, but
yeah.
Well, in that case, x plus y isn't going to work.
But let's just take the last line.
I wouldn't fixate on this too much. This was just me coming up with the most complicated thing that would fit on one slide, on one line of a slide.
Okay.
Of an example of a very complicated expression. Don't worry about it too much. Okay? Literally just an example. Now I'm feeling like I should have gone with something that wasn't the ternary operator, but there we are. Every expression has a type. there's another property of an expression, which is its value category. Every expression has a value category. And to explain a bit about value categories, which is really what Move Semantics is all about, we have to step back in time. Well, we don't have to, but we're going to. We're going to go back in time to C++ 98. So as I said, every expression has a type. The other important property of an expression was whether it referred to a named object, referred to a bit of memory in our program. And that historically was called its value category. And there were two possibilities in C++ 98, well, there are still. Either it does or it doesn't. So we've got two ints, x and y. X refers to an object. 42 doesn't refer to an object. It's just an ephemeral thing that the compiler inserts for us. Right? There is no location in memory where 42 is stored. This one's a bit more tricky. X plus y. For two ints, x plus y returns us a new int. But the return type of x plus y, unless we assign it somewhere, it doesn't exist anywhere. It doesn't exist until we assign it to something. Right? It's an ephemeral value.
So are you saying the compiler doesn't go with the computation for that? Or does it? I mean, it would be.
Plus y.
Huh?
You mean x plus y?
For x plus y, two ints, if you didn't use the result, it wouldn't.
It wouldn't get
No. If this was a custom operator plus and it didn't have the definition available, then it would, because it could potentially have side effects. But it wouldn't do anything with the returned object. So this is back in C++ 98 times. In fact, it dates back far further than that to the original KNRC. Things that referred to objects were called L values, and these ephemeral temporaries, we call them temporaries, were called R values. And the naming is pretty bad, but the reason is that once upon a time, L values were things that could appear on the left of an assignment statement, and R values were things that could appear on the right. Const, when Strauss invented const, and then that got into C, that messed up L values and R values, because a const value is still an L value, but it can't appear on the left of an assignment. It's can't assign to a const. But that's where the names come from, and unfortunately they sort of stuck. No, they haven't stuck, they've got a lot more complicated. So anyway, we can put these in a nice little table. Either it refers to an object, in which case it's an L value, or it's a temporary expression returning a temporary, which is an R value. Nice and simple. Those were the days. So the important property, does it refer to a value? Does it not? Does it refer to an object, sorry, or does it not? There is a second important property of expressions in C++ 11, and that's whether the result of the expression can be moved from. Okay? That is, it's not particularly obvious, but that is a fundamental, if you think about it a lot, and people did, they worked out this was a really fundamental property of expressions, whether you could move from the result or not. Now, if you have an R value, if you have a temporary, you have to be able to move from it, because otherwise it's useless. Right? If you have a function that returns an object, if you can't assign that object to anything, that's useless. What does it do? So R values can always be moved from, otherwise they're useless. But L values, it turns out, can sometimes be moved from. And the sometimes is the interesting bit. So our table gets a bit more complicated, because it's now got two axes. It's now a table as opposed to just. So we know temporaries that can't be moved from don't exist. But now we've got to come up with names for these three things. And we don't want to be too inconsistent with 30 odd years of C that went before, so we have to come up with names along the right lines. So if it refers to an object that can't be moved from, we call that an L value. And the properties of L values are generally as they were in the olden days. If it refers to an object but we are allowed to move from it, that gets called an X value. I think the X I read somewhere stands for expiring, but X values aren't necessarily expiring, so it's, in any case, it's an L value that we can steal the contents of. Sorry, like an X value that we can steal the contents of. And then finally we have the last box. We have a temporary that may be moved from, so this is a pure temporary. It's a pure R value, PR value, a pure R value.
Why not just a value? Yeah.
Why did they rename this PR value? It's because it turns out that the interesting properties are this one and this one. So that's why I said these are the two really important properties of expressions, whether it refers to an object, whether it may be moved from. And so they introduce names for this column and for this column. Oh, my table's building gradually, my slides aren't. So these two value categories together are called GL values, generalized L values. And in this row, they're called these things, X values and PR values. Things we can move from are called R values. You're looking like this is breaking your head.
It is.
Yeah. This, okay, I've read a story online somewhere that this whole proposal, this whole move semantics thing that people have worked on for years was almost scuppered at the committee level when somebody, I don't really know how it works, maybe they stood up in front of people like this and tried to explain this to the C++ committee, like the world's greatest experts for the first time, and almost nobody got it. Everyone went, what?
So don't feel too bad.
No, I'm on good company, yeah.
Yeah.
Maybe another way to think of it is you've got, you know what pointers, right? You have your base type like a int. So you have int star, right, which is an int pointer. And you know you can have int reference, right, so you have int and. So this is just introducing what's considered int and. And then there are a few cases where something is either automatically considered an int and, such as when it's on the right-hand side of the operation, or when you stood move it, which is internally actually just static cast to and of that type. You literally just use static cast if you wanted to achieve the same effect. And then you can then utilize that type because you can say, well, I have a constructor that takes T and. And then that T and constructor is considered a move constructor, so you just implement some alternative behaviour when it's the and type versus the just and type. And the same applies for operator equals. You have one operator equals is when it's type and, do this thing, steal points, whatever. And then the old existing stuff when it's a const T and, do the copy operation. Best I can do.
So, two important properties of expressions. Refers to an object, can be moved from. Refers to an object, can be moved from. Every single expression has one of these three value categories, only one. And the two most common you'll come across are these two, which correspond to the old L value and R value. And then we have these new magic things called X values.
And there are no more updates inside.
No.
Okay, that is it.
Yeah.
Yeah.
So this is a rather well-known little diagram. This is what saved the proposal. It's because apparently they went away, broke for lunch or a break, and Strausstrup or somebody on the whiteboard, I think it was Strausstrup, drew this and took it back into the committee and went, okay. You have an expression. Every expression is one of these three categories. But then we have these two sort of umbrella categories that.
A diamond.
Yeah. Basically, an X value is something that is simultaneously a GL value and an R value. This is one thing, that's the other thing, and this is both. Yeah? All right. If you think this is mad, don't, because I tried to do it earlier and it confused me. But the CPP reference, you know, if you've been to CPP reference, their page on explaining what an L value is it's a GL value that is not an X value. Brilliant, awesome. Anyway,
It's easy to remember.
is it?
I'm joking.
So the X value is like a frog.
A frog?
Yeah.
Why?
It's a joke, obviously.
Okay. Every expression has one of these three categories. Know your value categories. This is to help you out. If it has a name, it's an L value. Golden rule. If it refers to a named object, it's an L value. If you can take its address, it's an L value. Right? In fact, this is more or less the definition of an L value. If it's an object that's returned from a function, or rather, if it's a function call expression that returns an object, which is a better way to say it, then that's a PR value. It's a pure R value.
So what should functions return?
Function should return what's appropriate for that function.
No, what I mean is, I don't mean the type. I mean, should it effectively return a local instance of a local, which will get moved into?
That's one way of doing it. Okay, so functions can return nothing, void, in which case this doesn't really apply. It can return an object, like an int or a standard string, or it can return a reference. And in the case where it returns a new object, that is a PR value function call expression. So this is by far the most common way that you'll see PR values as a result of a function call. It might not necessarily look like a function call with brackets. It might be an operator like x plus y is a function call in disguise. And this magic function standard move is used to turn L values into X values. So by default, when we do Y, whatever I said earlier, A equals B or B equals A, by default that's a copy, because the thing on the right hand side is an L value. If we turn it into an X value with standard move, then we get a move operation.
You can turn a PR value into an X value.
A PR value?
Yeah.
No, you don't need to, because you can always move from a PR value.
Okay.
Can you turn a PR value into an L value by just giving it a reference?
Bind to it.
Binding a reference to the PR value, yes. In which case the reference has a name, so the reference is an L value.
But would it have to be a const?
It does have to be a const reference in order to. Why? Yeah, interesting.
Why would we need to enforce that?
Well, I wonder actually if they probably, unfortunately, people behind there can't really see if I scribble on this. Maybe I can move forward.
I can try to move the camera.
I wouldn't, because it's all.
Watch out for you, just moving it.
What of the other part?
On the
move
paper,
the paper.
you're going to get behind it.
That doesn't look like it's got a thing at the
You're
top.
going to leave it there or move it out?
Can we squeeze it behind all the chairs? Sorry to be a pain. Should have prepared all this beforehand, but I didn't know people were going to ask difficult questions about a difficult subject. How could I possibly have known that?
Just to make it feel good.
How many one?
No, that's why. Oh yeah, I do these things.
Alright.
Well, never mind, it's here now.
Department of Redundancy Department.
Yeah. Right. Let's say we have.
We'll have someone in a second.
I don't worry about it. So we have this function void foo, which takes a reference to an int. And then we have another function called getInt. If we try to call foo with an argument of getInt, this is so getInt returns a temporary, returns a PR value. And if we try to call this function foo, which takes an L value reference with this PR value return, it's going to say no, I can't do that. And why is that? It's because the whole point of taking a mutable reference here is because you want to modify the object. And what's the point of modifying this? It's going to die. It's a temporary. So you can't bind temporaries to L value references. That's really rule introduced it when they first invented references in whatever it was, 1981 or something. You can't bind temporaries to non-const references. However, if we had a different overload which was that took a constant reference, then that would be okay, because if you've got a constant ref, what you're saying is I want to look at this value. And it's probably perfectly fine to look at the value of this. This might be, you know, get newest ID or something. And it's perfectly fine to look at the value, but there's no point in modifying it. That is going to be an error in your program. So this saves you making errors. It's worth noting, however, that you're saying that for all me saying this is a bad idea, Visual Studio historically has allowed you to bind mutable references to temporaries. I don't know if it still does because they've got a bit more strict about standards compliance, but it used to do this, which was horrible. And yes, hopefully it doesn't anymore. I don't know. You use Visual Studio, don't you?
I don't.
But you don't do that, so.
I don't do. I like to not do stupid stuff. I also like to build with Clang and GTC conformance, but they have been getting a lot better lately. Yeah. They literally just fixed __ C++, so it actually has the correct
saw
value.
That.
But you have to turn on the compiler option to get the correct value. Because some people apparently rely on it being wrong.
So in Visual Studio, this thing was compiling, and despite being potentially a flaw in the program, making a
yes.
result.
Yeah, it was. They called it an extension, but it was not a very helpful extension.
In Visual Studio, you can do so many wrong things. Like you can add 2 char literals. Like you can use the 2+ operator.
Yeah.
The plus operator and 2 char literals and acts like you're concatenating a string, which you're clearly not, because they are pointers. And that's counter map derivative.
The other thing is that an integer literal is an R value, right? Because it doesn't refer to an object in memory. So if we've got foo with 42, if we imagine this constant overload didn't exist, what you could potentially try and do is modify the value 42, which doesn't really make any sense to try and modify a literal, right? And there's a famous thing of an old bug in a version of Fortran that allows you to do exactly this.
So you get an error now if you do that?
If you try, so if we assume this one doesn't exist,
yeah.
Then that will be an error, yes, it won't let you do it.
It doesn't actually do anything though, because you could do int and x equals 42, and then on the next line modify it, it won't change. It won't make 42 become not 42.
Spoil all my fun.
Oh, sorry, okay.
Right, so where was I?
There you go.
So as a name, it's an L value, take its address, an L value, blah, blah, blah. So we can bind an ordinary reference to an L value. Oh, this is in the way of the screen now. Move that out of the way for a second. So int x equals 0, we form a reference to x and a const reference to x. Oh, that was all. Thought I was going to go further than that, but I didn't. So we can form a reference to int, which refers to this variable x, and a constant, the same thing. So you've all seen this lots and lots of times. This is all familiar.
Now, that's if we can actually see it.
Yeah, sorry, it has gone rather small, hasn't it?
Sorry.
I'll move the TV closer to you. I'm not sure how to boost the size of it when the slides are already done.
Open your eyes wider.
Yeah.
Yeah.
The telescope.
So can you change the value of x?
That's as far as it's going, I'm afraid. Otherwise we're going to lose power. I'll just rearrange the room. I mean, what could go wrong?
Can you change the value of x?
Yes, through this reference, not through this reference.
So if you change the value of x and read CR, you would get that.
Yes. So you can think of a reference as a new name for the original variable. Yeah? You've been doing this long enough, you've surely used references already. Sorry?
I don't like code that does that.
That's obviously point of scope. It's in the same scope, right? Usually you take a reference in functions, right?
Yeah.
Or possibly as a field in a class. Because it's going to be in a different scope, and then you need a way to access the thing you want to refer to. But obviously it's the same scope, and therefore not really very useful.
I feel like a weatherman standing like this. It's going to be cloud over southern England. Anyway. We also bind a const, this is what I was saying here, we can bind a const reference to an R value. So we have this function getInt. We can bind our constant ref cr to the result of getInt. And this will actually do something called lifetime extension. Doesn't really matter for ints, but if this was a more complicated class, if it was a string, it's called getString, then this temporary would live until this reference went out of scope. It's not really too important to worry about today, but
you can always just use a literal. You can put 100 instead of getInt. That would work as well.
yes, I just want to show a PR value from a function, yeah. Just to remind people that functions returning objects, that function call expression is a PR value.
Sorry, I have a question. I knew C++ 10 years ago, I knew these things, but I don't remember anything. What is the difference, if you can say it in short, between R and CR?
Up here.
Yeah.
So R here is a mutable reference, which means that we can change x via this reference. So we could say R equals 3, and when we did that, the original variable would have the value 3.
Mm-hmm.
Okay? But this is a reference to a const int. And if we try...
It's a constant and we cannot change it.
Exactly. So if we tried to say CR equals 3, the compiler would say, no, you can't do that. You can't assign to a const reference.
I mean, only when you first time assign that will work, but later on. Am I correct?
He means when you bind it. Yeah, the binding is obviously valid.
Yeah. Yes. Yeah. So this isn't an assignment, this is a declaration. This is creation. But we cannot bind a non-const reference to an R value. So this is the thing I was saying that doesn't work. If you try and do this, so we have our getInt function there. If we try and say our mutable int ref, which I've still called CR because I'm an idiot, equals getInt, that's going to say, no, you can't do it. Unless you're using an ancient version of Microsoft's compiler, in which case it probably will. But it shouldn't. And this isn't allowed. No, I'm going to keep it there because I think I've got lots on the next slide as well. Sorry, just give me a second. I'll carefully manoeuvre behind here. and get some water. So, C++ 11 added this new thing called R-value references. And we write them type and, ref. So, an L-value reference is written with a single and, an R-value reference with two ands. So, in this case, we can bind an R-value reference to an R-value. So we have our familiar getInt function. We can say int and RR. That's R-value reference, by the way. It's getInt. This works okay. And this will also do the lifetime extension thing. And then what? Sorry.
What can you do with RR?
Anything that you would like to do with an int. So you can modify it. The thing that I just told you was a stupid thing to do? Yeah, you can if you want. You would almost never write code like this. The time you would get an int and is when you use it as a function argument, function parameter.
Yeah.
So you'd never, I can't think of any good reason why you would write code like this. This is just an example. It's legal, but there's...
It's more like asking for trouble.
The only thing I could possibly think of, and this is a bit tenuous, which is pre-C++ 17, if you don't have guaranteed elision. So by making the type an R-value reference, it would guarantee that, I don't know, it's not a theoretically stupid compiler, that it wouldn't take the PR value and then again initiate the move constructor / copy constructor to put it in the left-hand side value. But in practice, that's pretty tenuous.
I've got a question.
Yeah.
Online. Does R-value ref takes memory?
Yes.
No, the object takes memory. The reference itself is internal to the implementation.
Potentially, yes. In practice, the compiler may well optimize it. It's implementation defined, I would say. Optimization defined.
If you use the value.
Okay, so what the thing is, you can modify the return value here. So it lives somewhere. It's got to be in registers or on the stack somewhere. There will be some bits for this int ref, somewhere.
Can do also const and then.
You can. It's not very useful. It's even less useful than just declaring a reference here. But
it's effectively the same as the other example there on the board.
Yeah. So
having a
const ref, an R-value reference to a const. They can turn up in a couple of situations. The only situation I can think of where they turn up is where you have in generic code where you are just blindly adding and to the end of a type, and that type is const something. So then you get const t and const int and.
Const vector of balls.
Maybe.
You had a const vector of balls.
I try not to think about vector ball.
Yeah, maybe you could say that. I think you could achieve.
I guess what I'm asking is, if you can modify the value, what's the use case for trying to modify the value there?
The use case, the whole reason this exists is not so that you can modify the value of a temporary directly. There's no point doing this and then going, okay, getInt gave me 4, but now I want it to be 3. That's as pointless as it was before. What is useful is because now this is modifiable so we can move it again. Right, so if this were strings, if it was a more complicated, more expensive type, if we had an R-value reference to a string, then we know that came from an R-value, and so we know we can move it somewhere else.
Basically, it's a way of having more information, because now with this and, you can know that the type you're taking is either immediately going to die after its declaration because it's a PR value, or someone has declared that they are promising they're not going to use it afterwards by using sort of move. And then that obviously enables you to say, well, I'm going to stick this thing in some unspecified state by taking stuff from it. So the idea is it enables you to optimize and implement alternative behaviours when you know an object's going to go away, so, straight after your call.
So we can bind an R value reference to an R value. We do it to a PR value here. Standard moves turns this L value into an X value. An X value is an R value. That complicated table again. So we can bind this reference to it. This works okay.
And then what can you do with X? In this case, X is an int, but if it was a string.
You could move it somewhere else. You know you can move it.
Moved X to RM.
Okay, but imagine here you're just declaring it as a stack variable, which is kind of imaginary. But imagine it was a function argument.
Yeah.
And then within that function, you know that you can move your argument somewhere else without incurring a copy.
Okay. So as long as you don't do anything with X, actually, right?
Yeah.
So say you have a function that takes in a stood string and add, right? So the string, the function's going to take that string and move the internal buffer, so that when it returns, the strings, that string obviously is some unspecified state, and you can't use it anymore.
Is there anything that stops you from modifying the value after? Does the compiler catch you trying to modify it or something?
It depends on the class and what its move semantics implement. So for stuff like vector, it's going to be empty afterwards. There's certain things you can call that allow you to legally reuse the same object. I think strings got the same thing. But it just depends on what it is in the code in terms of safety.
So this is really the key thing. We cannot bind an R value reference to an L value. Right? So if you have it as a function argument, you know that that thing is something you can move from. So an R value is something that you can move from. And we cannot bind an L value to it. So here we have int ref ri equals x. That is not going to work. It's going to tell you this thing must be an R value. And x, the expression x, is a name, refers to a name in the same scope. It's not an R value. However, up here, standard move is used to transform something into an R value. That's the point of standard move. So it's worth saying, actually, probably at this point, if I don't have it elsewhere, standard move isn't magic. Okay, it doesn't do anything that you can't do yourself. Standard move doesn't actually do anything, doesn't actually do any moving. All it does is it turns this, it changes the value category of the expression, changes it from L value to X value.
Wouldn't it, well, at least in this case, the same as creating a function which takes x and returns x?
No, because if you return x by value, that would be a PR value, and it would be a copy. What standard move actually does is it returns an R value reference, and if you return an R value reference from a function, that's an X value. But that's
because isn't it what get into does returning?
Sorry.
Isn't it what get into does?
So getInt returns a new object, and if you return a new object, that's a PR value.
Okay.
Pure R value.
Instead, if you get into was designed to take one parameter and return that parameter would be different.
Yes.
Okay.
If it returned, so I've talked about functions that return new objects.
Okay.
You can have functions that return references. That's different. They're not necessarily PR values. Believe it or not, I've tried to simplify this.
Can you return an R value from a function? Cannot.
Return an R value, you return T and back.
You can return an R value reference, yes.
If you're returning actual value, like the actual object taken, that is a PR value.
No value.
No, if you return by value, then obviously, because you're going to do like A equals result of function call, right? And then, even if I just call the function, I don't even use the object it returns, right? That object is a PR value. It's an L value, and it's going to live beyond the line. The return value of a function is a PR value. Okay? You can stick in something, and then the thing sticking is going to be an L value, but that result in and of itself is not.
So if you really want to know the gory details, if you return by value from a function, so if your function is standard string get string, then the value category of that function call expression is a PR value. If you return by L value reference, which sorry I've written a bit small, then the value category of that function call expression is L value. And if you return by R value ref, you might think that it's actually an X value. So again, I didn't want to put this in the slides because I thought it was needlessly confusing, but we sort of touched on it, so thought I'd mention it. The most important thing, because most of the time you want to return by value from your functions, if you return by value, that function call expression is PR value expression. It's just there for completeness if people are really that curious about it. This is, like I say, this is pretty hardcore stuff. This is not basic C++ anymore. So if you're sitting there going, what is all this? Then don't worry about it too much. Like I said, you don't really have to know absolutely exactly what an X value is in order to benefit from move semantics. This is for people who are interested and want to know the nitty-gritty of it.
So the final exam will be 100% of this stuff.
I'm sorry?
So the final exam will be 100% of question about this.
Oh yeah, it's just going to be a list of expressions and I want you to tell me the value categories. That's all I'm going to do.
But you can make one mistake.
I only to test you.
Yeah.
That was why I did that. But well done. People spotting it. There's one more interesting thing that I should perhaps say here. Quiz, value categories. What is the value category of the expression X?
L value?
It's an L value, right. It's got a name, it's an L value.
Yeah.
There's no reference.
No, but it's got a name. So if we just write X semicolon, it's an L value. What is the value category of RR? If we just write RR semicolon, that's an expression, well, it's a statement when you put the semicolon on it, but the expression RR. Several people said something at once. What?
I might be wrong because it's a pointer, but because the other side is a function and the function always returns a value, then I thought it's the...
Okay, so just imagine down here, we just said RR semicolon.
L value.
Why is it an L value?
Because it's got a name.
Because it's got a name. 10 points. Excellent. So this is the thing that broke my head when I was trying to first understand all this move semantics, is that you can have a thing with that has a type, its type is R value reference, but it's the value category of that expression, when you use its name, is an L value.
That was confusing.
That is the mind-bending thing, right? That's the thing that really hurts.
Is it not an X value?
If you have a name, you're an L value.
Yeah. If you have a name, you're an L value. Just remember that, and most things become easier.
So how does the value category affect your ability to remove it later?
Because you can only move X values and PR values.
Right, so you got RR in your example.
Yep.
If I don't immediately return RR.
Yeah. So if you tried to pass RR to a function,
yeah,
taking an int and,
yeah,
it's going to say no, you can't do that. Because you're trying to pass an L value, you're trying to bind an L value to an R value reference. That's the thing that really confused me. However, you can transform it into an X value with standard move, and then that will work. So you have to remove
Oh, really?
Yeah, R value references.
Once it gains a name, it becomes an L value again. So it's saying RR is an L value of type int and and.
Yeah.
I think one of the ways I define it for myself is you understand R values by omission. If it doesn't have a name, then it's an R value of PR. But once it has a name, then it is an L value.
Yeah. Things without names, pure R values. Things with names, L values. Things with names that we've transformed into R values are X values.
It's ridiculous, to be fair.
It is incredibly, it's easily the most difficult to comprehend thing in modern C++. Luckily, you can get most of the benefit without ever having to really care about what an X value is.
I think the best way to think of it is just in your head. That's what I do anyway. So you go, would this thing be and or and? If you just take those those two distinctions, it becomes a lot easier. So, it's not just right hand side, oh, it's an and.
But see, now you have to make a distinction between the type of it and it.
Yeah.
That's not so hard because it's something, it's a variable name. This thing's named, so it must be an L value. So it must be an and, right? It's got a name, it's an and.
Sorry, and?
And how
Yeah,
often do you have to use that? Because I presume this is very advanced stuff, yeah? So is it like you will find this like every day and you have to really, go through the pain, or is like at some point, when you start growing like a very long beard and then you can start actually thinking about that?
Well, he doesn't want to be
It depends what you write, like if you're writing a simple or you're writing games or complicated code.
Yeah. Whenever you write a type that has a copy constructor and a copy assignment operator, you should also write move operations for that type.
That's what I was expecting.
Well, that's the most common time. That's the most common time you're going to see R value reference types.
And this confusing bit is when you implement those move functions, you're getting in the type as an R value reference, where you're using it as an L value.
Yeah, because once it's the argument to a function argument has a name is an L value.
Yeah. That's it.
Yeah.
Okay.
Because you know what it is, that means you can say, I'm going to do certain things I wouldn't otherwise do. There's a copy constructor. The copy constructor is not going to say steal pointers and bind reference on it. This time, all that happens.
I think a general rule that I read somewhere is always depend on the sort of constructors the compiler generates for you. If you write one, then it's very likely you probably have to write the others. Is that a...
Yeah, so we'll talk about it in a bit, but the rule of 5 is what they call it.
Rule of 0 nowadays.
Well, we'll get onto that as well.
It was on your slides, I think, a week before, something.
The rule of 0, the rule of 5. Yes, I talked about it months ago when we were first talking about copy constructors. I said, by the way, there are also these things called move constructors that we'll talk about sometime, and this was the day. So it's only taken, probably about 20 weeks of doing C++ to get you lot to the stage of being able to do this. So congratulations. I'm not sure none of you were there for maybe Laurent was there right at the start. Were you, Joshua?
Probably.
Yeah, you've been coming for a long time as well. Anyway, let's move on. R value references and overloading. This is why you want to use them, what they're most useful for. Remember, R value references can only bind to R values. So if a function takes an R value reference parameter, we can only pass an R value into that function. So, I'll try and not trip over wires and things. So if we have a function called foo, and it takes int and then I, if we call foo of 42, then 42 is an R value, that's okay. But if we say int x equals 0, and then foo of x, that's going to be an error. And the reason for that, well, can anybody tell me what the reason is?
It's no null value. It's no null value.
Yes.
So because the zero is what was the something was with zero, I can't remember, with numbers. If it was like one or above.
Okay, let's not use let's use string. And this, got rid of that. String x equals. Do you know what? I'm going to do it.
Okay.
Yeah.
Sorry.
Right. So now we have our function void foo. Takes a string and. If we call foo. I don't know why I wrote standard this time, but you can pretend it's there. So now we're calling foo with this, we're calling constructor. This is a temporary value. We pass the temporary into here, that's fine. That's okay. However, we now create a string s, and we try to call foo of s like that. That's going to say, no you can't.
Because the type is string and the other one is the end.
It's because this thing
doesn't expect string, it expects
this thing is a PR value. So this thing will take and only accept R values, and this thing we're giving it is a PR value, so that's okay. However, in this case, S is an L value.
That's because it has a name.
Because it has a name. I'm going to put one more thing on the bottom in a second. So in this case now, S is an L value, and it's going to say you can't pass an L value into this function, because you can only pass R values into there. So how, if we have this string S here, and we want to call foo with S, how can we do that? Sorry? Move it, exactly, because what does move do? Sorry? Turns it into an R value, precisely, yeah. So we can do foo brackets move of S, like that. I'm sorry that your first session was so complicated, but thank you for coming.
We are starting in May.
Yeah, so 1st of May?
1st of May
The 1st of May we're going to begin again from the beginning, so you won't have missed anything. You can.
I'm actually interested in like doing game programming with C++.
Okay.
Something.
Not specifically, we're more sort of general C++, but yeah, we're going to have the syllabus online, the new one, very soon. So if you've seen our website,
Hope to see you again.
yeah, that'd be awesome.
Yes,
Thank you for coming.
it will be. Thank you so much. Bye.
Yes.
Have you found someone who can explain this better than me?
No. Sorry, there's something else I was wondering. So I have a question.
Mm-hmm.
So if you gave void, say change the signature from void to string, stop, I think ampersand.
Change the type here.
Yeah.
Okay. That's the return type.
Yes. And then imagine in foo, all it does is return whatever it gets.
Yeah.
So outside the function, whatever you pass it has to be an R value. Inside the function, it's an L value.
Mm-hmm.
And then after the function, it's a X value.
Okay.
You have to return std move, like you do, you should return std move of X or whatever.
Actually, I'm not sure. I was just about to say I'm not sure that you do have to do that because return automatically.
I think it works with random time. It's move only. I'm not sure.
Okay.
Return value literally is out.
Just do it on Google quickly.
You're cheating?
You almost never want to return an R-value reference from a function.
Okay.
Very rare that you want to do that.
So you just return.
Return by value instead, yes.
I believe I am correct. You have to still move it.
You do. Okay.
Very good.
So effectively, once it becomes an L value, you can only, in a general sense, you can in the return you can only effectively say take the value of it. But then on the receiving end, you do the standard move, or you rely on the binary move for it. So you pass in an R value.
Yeah.
You just do a return, which effectively returns by value.
Yeah.
Yeah. And
What's the return type of function?
return type of function is well, because we said we can't have.
So you return by value.
T or T and N.
Well, just T because we don't.
Let's say yeah.
Yeah.
You don't need to move.
Yeah. Don't need to move, but the compiler will
Move for you in a
move
return. If you return by value and you say return this thing,
yeah, it'll do the move for it.
it'll do the move for you.
Slide it.
Yeah.
And if you try to return it by, can you return it by ampersand?
Correct. You could, but you'll crash because obviously, well, if the object lives inside the function, it will happily return a reference to the object inside it, but it will already gone out of scope, and now you've got dangling reference.
But if I'm only returning item that was passed in.
Oh yeah, if you just return what was given back to you, then yeah, of course. Okay. You're just casting off it. Which is what literally submove does, submove is just a function. It casts what's given in.
Cool. Sorry, I know.
Right. So where were we? I've lost my. So if a function takes a non-const L value reference parameter, we can only pass an L value. That's what we said. And then we have this final horrible mixed case, which if a function takes a const L value reference, then we can pass an L value or an R value, because R values can bind to const references. So theoretically, if we have foo string and we have foo const string, if we have these two overloads both in scope, then when we call it here, both of these two functions are valid, right? They're both okay. Fortunately, something called overload resolution comes into play, and it decides it likes the R value one better. So if both of these functions are available, when you pass an R value, it will choose this one. When we do this, well, in this case, it can't call that, so this one's the only one that's available.
Did you distribute? That's the same as the first one?
Yeah, both of these will be available, but it will prefer that one. Because the standard move gives you an R value. Can I move this back again? Yeah. Rather than stepping behind the TV the whole time. So an R value reference version will always be preferred when called with an R value argument. So let's not overload you all at once.
Check. I'll take a photo for people. So this one, and I put different color. Maybe you can do, let's say, number 1, number 2, and then just give the numbers to the others.
Sorry, say again.
So if I take a photo, so people can say, let's say, put number 1, number 2, and when the numbers will apply, so that people can, when they look at the photo, they can have a look and see which one they will apply to.
Yeah, I wish I had another colour.
Yes, this one doesn't work.
Is there any residue?
So this one can work with 1 and 2, yes? Thank you.
have the std string hello,
Yeah.
that is a value of type string.
Yeah. PR value.
Yeah, PR value. If you have any of the other basic types like int, float, char, can you write it like that as well? Say int 2 or
Yes,
yeah.
yes you can. Yeah. You have to be very careful of something called the most vexing pars when you do things like this. So if you can avoid that by putting curly braces in there instead of the round brackets.
Okay.
But is there any game? No.
Yes, because you avoid this awkward.
Vexing pass.
Okay.
So a simple example is that you're doing just a
What?
string S parentheses thing, semicolon.
Okay.
If you use curly braces, unequivocally you want to instantiate the string. If you use parentheses and you've got to include string, you're declaring a function now,
Right.
which you're probably not wanting to do.
That's the same thing.
Do you know curly braces and a series of chars for a string?
Yeah, it's initializing. It's a PR stood string, so it's a PR value stood string class, and it's calling the constructor.
I know what you're saying. You're thinking of the vector curly brace
Yeah,
constructor
yeah,
that takes a
yeah.
sequence of
Because
T.
a string is basically a special case of the vector.
Yeah, I don't think a string has an initializer list constructor.
And even if it did, you use two curly braces. You use the outer curly braces to represent calling the constructor, and then an inner set of calling curly braces to represent the initializer list.
Okay.
What? I've not heard of that implementation before. Is that just for string or?
No, it's not for string. I'm saying if it did take an initializer list, it doesn't take one. So you can
Oh, I see.
Right. This has all got really complicated, so let's look at some actual code that makes it really, well, no, simpler. We have this function, insert into vector, and it takes an L value reference to a vector and a const L value reference to a string. This should be kind of familiar, right? This is not mysterious at all. And what it does, it calls vec pushback string. So, pretty a pointless function. We could just call vec.pushback, but it's a demonstration. So this is a const reference. It gets copied into our vector. So now we have a main function. We declare a vector and a string here, hello world. We insert s into our vector. That's fine. So when we call this reference binds to s, we push it back, that's all fine. That's C++ 98, no problem at all. When we call this second one, what we're doing is we're creating a temporary string. I've done it very explicitly there. You could actually just put the string literal in, but I've made it explicit that we're creating this temporary. We're creating a temporary string.
Which kills the world.
Sorry?
Which kills the world.
Goodbye.
You say hello
Goodbye,
world, and then
Oh, goodbye world, yes, sorry, pretty slow. Yeah, it's been a long day. This is a temporary, but a temporary can bind to a const reference just fine. So this gets lifetime extended in there, it gets copied into the vector. At the end of this function, the temporary dies. This works fine. Again, this is C++ 98. This is hopefully.
And would that be instead error if it was not constant?
Yes, if this was a mutable reference to a string, if const wasn't there, then this second line would be an error.
Okay, cool.
Yes, good. So what happens now? Fortunately, the text is going to get a little bit smaller. I'll move that closer. Not too close because I'll unplug the TV. So now we're going to have our first function, our first overload just as before, and we're going to introduce a second version of this function. This takes a string and. Okay? So this is one of the examples where you might use an R value reference. It's usually used in combination. And we call vec pushback bracket standard move struct. Why do I need to use standard move there?
Because
because str is an L value because it has a name. So we have to turn it back into an R value to pass it to pushback. Now, if you look at the vector documentation, pushback does exactly this. It has a const ref overload and it has an R value reference overload. So when we pass it an R value, it's going to choose the R value reference overload.
Just a side question, what's the difference between pushback and placeback?
Like void.
Sorry? Yeah. So if you in placeback, we'll call the constructor of whatever type is in there.
Basically, with pushback, right? So I have a class, and if my class constructor takes 5 arguments, start and stuff. Okay. So usually with pushback, you have to construct the object yourself, and then you can push that object into the vector. So you can have a move constructor, it's probably quite cheap, it's not that bad. In placeback, even better. Now I don't have to construct an object. I just literally inside the placeback parentheses, I just write the arguments that I want to send to the constructor, and the vector just does that in place. So I don't have to move one in or copy one in. It's just created inside a vector.
So we've now written a second overload of insert into vector. So now in main, I'm going to do the same thing again. So I'm going to insert into vector vec, comma s. S is this thing here. Which overload is this going to call? 1 or 2? 1, 2. Hands up for 1. Okay, hands up for 2. Nobody. 1. Well, you're right. You're all right. Everybody who said 1, it's because S is an L value, and so it can't bind to this thing, so this is the only one we have available, so it's going to call that one. What about this? What's it going to call? Who are you going to call? 1 or 2? Hands up for 1.
2.
Hands up for 2. See, you've all got this. Yes, absolutely. This is going to call the second one.
Ask us tomorrow.
Yeah.
Exactly.
Why?
1 in 5 minutes.
Yeah. Why is this going to call the second one?
Because of the cast. Well, because of the STD.
Which?
Cast to X value.
So an X value. An X value is an R value. Both of these, because it's the const reference, both of these are acceptable, but it likes the second one better.
So there is a priority? Or?
Yes.
Okay.
Something called overload resolution. Where there are multiple functions that, and this, it doesn't just happen with R value reference, it happens in lots of situations where you have multiple functions with the same name that are appropriate, it ranks them in order according to some very complicated criteria, and it calls the best one.
Okay.
And sometimes it's ambiguous which the best one is, in which case you'll get a compile error. And sometimes it can be quite surprising which one the compiler thinks is the best one because it doesn't match your intuition. But
is there a way for me to alter the order?
yes, but I mean not directly. You have to do some programming tricks.
Okay.
But there is a way to influence overload resolution. Yes.
Just a funny question. Because I know C chars are convertible to strings.
Yes.
Directly, if I pass the string, if I pass the literal string to it, what would it do?
Okay, so well, let's just look at this final one first. So what's going to happen in this case? 1 or 2? Hands up for 1. Hands up for 2. Everybody, excellent. Right, because this is a PR value, which is an R value, so it prefers the second one. Again, both are valid, prefers the second one. All got the hang of it. This is brilliant. Excellent, well done. What would happen if you just put in hello? So if you didn't have this standard string bit and you just put in hello world, just a string literal, what it would do is it would look at these and go, okay, I can't pass this type directly, but can I convert a string literal into a string? And it will say, well, yes, I can, because it's got an implicit constructor. And then it will go, okay, so if I call this implicit constructor, I'm going to get a temporary. Temporary is a PR value, so it's going to prefer the second one. If there was a third one of these that was void insert into vector, that thing, and then const char star, So a version of this that took a const car star directly, then again, overload resolution would come into play, and it would prefer the const car star version because no conversions were required, or at least no user-defined conversions were required. Whew. You've all got the hang of that. This was kind of the takeaway from this, from me yapping all evening. Now that you understand how R-value references are passed to functions, can reveal the magic is that these exact same rules apply to constructors and to assignment operators. Okay, so it means that we can write a constructor that takes an R-value reference as a parameter. We can also, usually when we can write a constructor that takes a const L-value reference, and we call that a copy constructor. If we write a constructor that takes an R-value reference, we call that a move constructor. And as I say, these complement, they don't replace, they complement the copy constructor and copy assignment operator. So, I'm going to sit down and demonstrate to you some copy constructors and copy assignment operators, because I've had about 10 slides of examples, and I thought that's, I'm actually just going to do it live, so I can modify it when you ask me questions.
Just to fault the homework, we have the homemade unique pointer repo, probably a decent way of practicing.
I've forgotten about that.
Yeah.
Well, that would have made a good example had I not wasted an hour trying to come up with one earlier.
It's on GitHub and our GitHub.
Right. Let's see if this works. Can you see that? No, of course you can't. And I don't have the option to share the display for some reason. This worked when I tried it a couple of weeks ago. How do I get the...
You want to mirror or?
Yeah, but usually I get a nice little...
It should be on. Is it on the other?
Yeah, it's not on my laptop screen either, so this is going to be fun.
Okay.
I think sometimes you get more options if you do sort of, is it like special key and P together I thought there was a special hotkey in Max that would give you a better presentation.
Show mirroring options in the menu bar when available. Mirroring options not available.
For some reason.
Right. Okay, so this means I'm going to have to try writing this over my shoulder, which could get interesting. Okay, first of all, can we read this?
Yep.
Tristan, do you want to move the desk for you?
We're going to move the table again.
Right, that'll do.
Is this Goldball?
No, this is
Wobbles.
no, no.
Jupiter.
One more time. What do we use every week?
Starting with C.
Oh, C line.
Yeah. Right, so I'm going to write this type my type. It's got default constructor.
A default constructor, in fact.
A defaulted default constructor.
we have to state it's the default one?
No. You could.
That was just saving some time. I'm going to have a massive crook in my neck tomorrow. Right, so we have the struct my type, which is never used. And we've written a copy constructor and a copy assignment operator. Everybody seen this? Everybody familiar with this? Right. So let's instantiate a my type, and then we'll write a second one. So we're going to construct it. What's going to happen here? Copy constructor, and here, copy assignment. Right. Fingers crossed, that is exactly what's going to happen.
I forget now, isn't it strictly the case that on line 23 you are technically, first of all, default constructing B and then invoking its copy assignment operator?
No.
No.
Are you testing us?
No, they won't actually, no compiler's actually going to do it, that's why I said in the strictest sense.
Yeah.
No, that's not happening.
I don't think that was the standard.
No, well, because since you have a copy constructor, that would be that's the semantics of it.
Yeah.
The difference is this won't consider explicit constructors.
Okay.
But you never write an explicit copy constructor anyway. So as you can see, when we run this, we get exactly what we thought we were going to get. Copy constructor, copy assignment. Okay, so unfortunately the compiler is going to...
How about then reverse B to A on the line 25?
Do you think that'll work?
I think so. Yeah, I think that will work.
Sorry, can I see your typing?
Sorry?
The typing.
Yeah, I'm really bad at coming up with names. So.
Sorry, from moving from A, so sorry, the previous one. Now
So this one?
No, line 25, I just direct you to do the wrong thing. So basically once we move stuff from A to B, so A will become empty. So now we want to move from A, which has got the stuff, now back to B.
What do you want him to type?
Yeah,
I mean, all it's doing is invoking a function and it's printing something. So it's not, the move semantic isn't actually doing anything in this case. Because it's a struct with no fields, right? But there's nothing to move. It's just calling to see out.
Oh, okay.
I'm going to change this back to what it was. Like that. So, all I've changed now is I've added this standard move. Okay, so first question, is this going to compile?
No, because you have to implement in that constructors since you've already done.
Okay. Josh doesn't know. You said your immediate reaction was yes. Okay, hands up for yes, this is going to compile. Hands up for no. Hands up if you're really bored and just want to go out and get more pizza.
I'm not bored, but I don't know. I wasn't sure either.
Okay, the moment of truth, what's going to happen? Why doesn't it do this?
Oh.
It compiles and it runs just fine.
Well,
So,
rule of 5.
No, it's a move operator.
okay, so now we go back to thinking about precisely what standard move does. Well, in fact, it tells you passing the result of standard move as a constant reference argument, no move will actually happen. So this is going to invoke the copy. What's going to happen is this is going to give us an R value. and it's going to look at the available constructors, which are these two. Well, the default constructor is obviously not appropriate, so it's going to look at this one, and it's going to say, can I bind this temporary, this X value that I have, can I use it there? It's going to say, yes, I can. So, okay, I'll use it. It's exactly the same rules as we were talking about for functions. Constructors use exactly the same rules. So this compiles just fine. It doesn't do what you want it to do. It doesn't move A, which is exactly the warning we're seeing here, which is rather nice, I think. I hadn't seen this before. I didn't know that was going to happen. So there we are. And we get exactly the same situation here. So we're probably exactly the same warning, yeah. In this case, we're changing B into an X value. It's going to look at all the available assignment operators. There's only one. It's going to say, well, can I convert the type into this? Yes, you can. And so if I can remember no, that's find and replace, whatever the shortcut was for run. It's not that one.
Control F9 or 10?
It's different on a Mac. Because they're stupid. But anyway, this also works just fine. So if you have the whole upshot of this is if you have a class from have some old C++ 98 code that just has a copy constructor and a copy assignment operator, everything is going to work just fine. You're not going to get any benefit from the move operations, but everything's going to compile and everything's going to work just as it should. Yeah.
Finish what you're saying.
So that's what I was saying, that a move is an operation that potentially modifies the source object. But in this case it doesn't, and that's fine. It means we don't get any benefit, but it doesn't do any harm either.
So if you gave it the move constructor and the move assignment operators,
which may or may not be what I'm about to do.
Okay. I think that would still be fine, because you don't have any data. You don't have any data.
Are you happy now?
It'd be more
In fact, this is
Would still be fine.
just a unique pointer that mess it around.
okay. This is.
Well, it won't.
Let's actually make it a bit more realistic. So this is how you write, or you would write a copy constructor, right? You take in the initialize list, initialize my blah to others dot blah. And here, oh no, can't put that. You would say okay. Yeah. Right, so what we're doing in here is we're copy assigning, I've lost my mouse pointer, copy assigning our blah, you can really make it explicit like that if you want to, our blah, copy assign other dot blah. Okay? So this is a slightly more realistic example now, very slightly. And as you can see, when we try to do move operations, it works just fine, it doesn't give us any benefit. So I'm going to change this back to what it was.
If you had the B in brackets,
Yeah.
does that result in a temporary?
No. So an expression in brackets is just the expression. Yeah, brackets are about ordering. There is one situation where it makes a difference, but I don't want to go into that. It makes a difference in decal type, but just ignore that for now. I don't want to delve down that rabbit hole for now.
Basically, our value reference to the type, right?
The name does, yeah.
I mean, the result would be in parentheses is now value reference to B.
Yeah. So let's now go and add. That's the wrong button. add a copy constructor, add a move constructor to this. So, what do I write?
My type ampersand.
I type and other, and then what? Right, so what do we initialize blah with? Excellent. Excellent. So other has a name, it's an L value, so if we want to move some of its contents, we have to explicitly say we want to move it. That is complaining that move constructors should be marked no except. Yeah, they should, but since we haven't talked about no except, I'm just doing this to shut the compiler up, which is, you know, what all good programmers do. Let's write the move assignment operator as well. First of all, note that the move assignment operator, like all assignment operators, it returns an L value reference to the thing it's operating on. It does not return an R value reference. So again, take an R value reference to other. Now what do we do?
This blah equals standard other blah. See how?
Yeah.
Return this.
Yes. That is a perfectly great way of doing it. The other thing that you can do. Who said that? Yes, absolutely, brilliant. We can swap our blah and other blah. And you think, well, what's the point of that? Well, there isn't really a lot of point with strings, but if we had a unique pointer, for example, then when we swap them over, other is about to go out of scope, it's expiring, it's dying, it's an R value, it's a temporary. So when we swap them, then other's destructor will run afterwards and it's going to destroy the thing we were holding.
But yeah, I was always worried about this. Doesn't blah take, or doesn't take it, doesn't swap takes references, so it's fine.
Yes.
Bear in mind you're going to affect the behaviour of your program fairly differently. So if you would like for the thing you're moving from to just be destroyed ASAP, then don't swap it.
Oh.
Potentially. Because if you swap it, right, the old object you just moved from, you don't necessarily know when that's going to out of scope. They won't use it anymore, but they might have a big long scope. Okay. And now that thing's still sitting there taking up memory because you swapped it instead of releasing it.
Okay, so if I can, I assume I've typed everything right. What's that? Oh, no accept again. Okay, yes, sir.
Sorry, explain that again.
So in this case, when we're moving, right, you say you said in his example, in theory, it could be a unique pointer, or it could be a string. String can be make sense, right? So you have two objects, right, A and B. You move from B into A, and you full stop. So let's just say it's a string, right? They both contain a megabyte of string. Then it's going to swap them over, and it's only going to get rid of the string when B finally goes out of scope. So for me, I say that applies to both of them. But in terms of making a memory saving, if you're moving from it, you could not swap them. You could just move the string into A, and then obviously the other one is now left with nothing. And you don't have the memory is not still allocated. Because if there was anything in A before being moved, it gets thrown away before grabbing the pointer.
So, what's going to happen when I compile and run this program?
Same as before.
which was, what's it going to print out?
It's going to do It's going to do a normal constructor. The normal constructor's default, so we'll print anything.
Yeah.
It will print a copy, and then it will also print assignment.
Copy assignment, yeah, absolutely. I haven't moved anything here. Right, so when I run this, I don't know why it keeps coming up. Oh no, it's working this time. We see copy constructor and copy assignment. Now, it surely won't surprise you, but if I do that, and I run this now, we're going to see move constructor and move assignment.
You know, is there a proposal, instead of having this verbose STD move, you just have an arrow in front of the equal sign, so you can...
That would be lovely.
Yeah.
Unfortunately, standard move is very verbose. Yeah, there was a proposal to add an operator which did the equivalent of standard forward, but which we haven't talked about yet, and we are running out of time. But the committee didn't like it for whatever reason, didn't get anywhere.
Wouldn't it be confusing with less than or equal to?
With what, sorry?
Less than or equal to?
Yeah.
It would be confusing with less than or equal to.
Less than or equal to, yeah.
Why confusing is in the other direction? The arrow, you mean?
Oh, so if you had a...
Backwards arrow.
Yeah, I'm not sure exactly what... Are you saying that they should do that?
You mean a tick arrow?
Are you saying like that?
Yeah, with an arrow.
But that is the tick arrow, you can
Yeah, something like that.
Yeah, unfortunately this is already valid syntax. This is saying, make me minus this, is that greater than this thing? Except in this case it's a syntax error, because my type is neither a numeric nor a pointer. But this is valid syntax as it is, so they'd have to come up with something new.
The other way around, what equals it, and then correct it.
So the proposed syntax I saw did that, I think, or it might have been that. But whichever one it was something that wasn't used before. But whatever, it's not happening, so it doesn't really matter. Right, so that's nice and easy.
Got a question.
Yeah.
What if you then try to do something with the column method on the would it stop compiling?
No, it will just blow up when you run it.
Void foo, my type, and it's just a function that doesn't do anything at all. So if we try to call foo b now, yeah?
You compile fine.
That would be fine because it's const.
Yes. It will compile fine, but is it doing the right thing?
It's semantically wrong.
Precisely, it's semantically wrong because we've moved from B. B is in an indeterminate state. So, as you can see here, we get this very handy warning saying B was used after it was moved. We can reinitialize B to, let's just do that. And now it's not complaining anymore because now we've reinitialized B. So now it's okay to use. What constructors, or what's this going to do, by the way? That's going to be the default constructor, yeah.
It's going to do assignment?
Yep. Which assignment? We've got two assignment operators.
It will be the no assignment.
Oh, we've got conflicting. You're going to be the tiebreaker. What do you think it's going to? You think the const one? Not the const one. You think it's going to use the move assignment operator?
That's an R value.
Yes, exactly. This, we're now creating a temporary, it's a PR value, so it's going to prefer this assignment operator. And
Something that's been worrying me since Move came around is, doesn't it change the semantics of the way you write data structures and algorithms?
I guess.
Like lists and trees and all of those kind of things, you have to be careful how you write them.
Careful in what way?
Well, because before we were just used to copying things around.
Yeah.
But now you have to be careful for the semantics of the algorithm or the data structures. You have to be careful what you specify.
If you choose to use move operations, you have to, in general, be careful not to use something after you've moved from it. Yeah, that's another reason why move is deliberately so verbose. So it stands out in your code. So when you're just scanning, you can say, oh, this thing has been moved from. Whereas if it was just a little operator, it might be harder to see. That's what I think the reason is anyway. Okay, got a second overload. You already know this. Which version of foo is going to be called here?
The constant. The first one.
Okay, so this is going to call
1.
1, correct. Is that going to call? Well, I've just told you because I'm an idiot. That's going to call the second one.
No, you wouldn't. Now we will.
Foo. And because you've already demonstrated that you've got the hang of this one is going to call 2. Perfect. Awesome. Now we're going to make it even more confusing. Right. What's going to happen? Doesn't even let me finish. Yeah. This is going to call the copy constructor. It's going to call the move constructor. Okay, so it's going to see this. It's going to say, let's call that. Just give that an argument. It's going to say, okay, I have to construct this new my type from this argument. The argument is an R value reference. It's going to look at the constructors it's got. It's going to say, okay, I prefer this one. And finally, this time we're going to default construct followed by move construct. So I don't have a marker on the default constructor, but if I did, you would see that happening. So hopefully we'll see copy construct, move construct, move construct. So that's what happens if you take a type by value. Whew. Right, I'm really impressed, guys, that you seem to get the hang of that all so quickly. Maybe not the X values and all of that, but like I said, you don't really have to know the detail, the nitty-gritty of that just to be able to benefit from move semantics. So, that went pretty well, that bit. Sorry, I know this is just so much of me talking today. I'm sorry. I would have preferred to have you doing all that. I just didn't prepare finish preparing the exercise in time. It's the rule of 5. Talked about this yonks ago. If you declare any of these things, then you probably need all 5. Okay? You can declare them equal or define them equals default, in which case the compiler will try and generate one for you. But the takeaway is, if you write one, you probably need all of them. Oh, got tiny text again. So, in some circumstances you can automatically get, the compiler will automatically generate a move constructor and a move assignment operator for you. In fact, when I say in some circumstances, by default, if you do nothing, you will get a move constructor and a move assignment operator. And the default versions will simply move all of your members in turn. So if you think about the compiler generated, the default copy constructor, compiler generated copy constructor, all it does is copy all of your members in turn. And the move constructor does the same thing, except it moves all of your members in turn. So that's brilliant. However, if you declare, what I was saying before, if you write any of these, you probably need all of them. If you declare your own move operations, then that will stop the compiler from generating copy operations. Because it says, okay, this person probably doesn't want this type to be copyable. Because move-only types, things like standard, what's it called, unique pointer, very useful to have move-only types when you have a handle to some object that you can't copy. Single ownership, exactly. So move-only types, so that if you write your own move operations, the compiler will say, okay, they don't want copy. The opposite, unfortunately, is also true, that if you write a copy constructor and a copy assignment operator, it will stop the compiler from generating move operations. And the reason for that is, again, this rule of 5 idea is that, well, if you're doing something special in the copy constructor, the default move operation probably isn't appropriate. So it's a safety thing. You can restore the compiler generated one by declaring it and saying equals default. We talked about the rule of 5. What's much better is the rule of 0. So if you don't declare any of these special members, if you don't declare copy constructor, move constructor, copy assign, move assign, don't declare any of them, the compiler will do them all for you and it will get them right, usually. As long as you're not dealing with pointer members and things. If you're dealing with, if all your objects are value, your members are value types, the compiler's version is going to be optimal. Rule of 0, that's the thing. I have, what do I have? 5 more slides, all about forwarding references. I don't know if you're all just terribly bored and we should call it a day.
Let's continue.
You want to, yeah? Okay. Sure. Sorry?
We're mesmerised, Karen.
You're hypnotised, yeah, just, you know,
It's not an easy class, but...
This is probably the most advanced stuff we've done so far. That's why it's right at the end of the course. I'm just going to tell this one to appear a bit at a time. So, forwarding references. Template argument deduction. See, now this is getting even more in depth now. Template argument deduction. If you remember when we had our couple of classes on templates, when we have a function template and a class template constructor in C++ 17, but we'll only worry about function templates for now. If we have a function template and we pass it a parameter, we pass it an argument, function argument, the compiler will try to deduce what the template arguments are from the actual argument. So for example, we have a function template foo, takes tref. I've an int I. We call foo with I, and t is deduced as an int. So we're passing an L value I, t gets deduced as int. That's pretty simple, right? That's pretty much where I left it, I think, when we were talking about templates before. We can also have a constant, ci, and we call foo with ci, and in that case, t is deduced as constant, I think. It's pretty uncommon that you'd want to do that. So we have these new things, forwarding references. So if we have an argument, an argument to a template function that is spelt t-ref-ref, where t is a direct template parameter of that function template, you've got a function template. In its argument list, you have t and. So it looks like an R-value reference. Unfortunately, or fortunately, depending on whether you're the people who designed this, it's not necessarily an R-value reference when deduction comes into play. So just to give you, I was going to write an example on the board, but I see I've got one on my next slide. Yes. So if we have t and we pass it an L value, then the template parameter is going to be deduced as an L value reference. And if we pass it an R value, then t is going to be deduced as the value, and the argument is going to be an R value reference type.
Why is it like that?
So it's like that to enable something called perfect forwarding. I admit it's a really confusing rule, because it means that this syntax, t and m, effectively means two different things. Because normally, vast majority of code, if you see that, it means R value reference.
Yep.
When it's a direct template parameter, it means forwarding reference. Yeah. Some other material calls this a universal reference. That was the older name for it. Scott Myers, for example, gave a couple of talks where he talked about universal references, but they've since renamed them to forwarding references. Yep. So I'm going to just, to avoid scaring you by showing you all the code at once. So now we have a function template foo takes a forwarding reference. This is a forwarding reference because t is a direct template parameter. I keep saying direct, and I'll tell you in a minute why I keep saying that. So now we call foo with I. What's the value category of I? It's an L value. And when we pass an L value into this t and, it means that t gets deduced as int ref. So t is an int ref, and then there are these complicated reference collapsing rules, and it means that little t here, the type of little t inside this function is L value reference to int. Okay, so what happens is that t is deduced as an int reference, and then little t has type int reference ref, and there are some funny reference collapsing rules. So if you try and add and to that, that's just going to come out as L value reference to int. Again, this is something that really hurt my head when I was first trying to learn about it. But if you're really interested, you can look up the reference collapsing rules, is what they're called.
How long it was?
Sorry?
How long it was when it was giving you pain to know how much it takes to go out of the trauma?
I'm still not over it, I'm still scarred. So the reference collapsing rules go like this. So if we try to take an L value reference to an L value reference, we get another L value reference. We can't take a reference to a reference, they just collapse together into a single ref. Okay? So this is the one from C++ 98. T and I'm taking yeah, I can't draw ands either. So if we now have an L value reference, and that's supposed to be 2, sorry. If we try to add an and to something that's already referenced, what we get is still an L value reference.
I want to say something about having a T and Y, so I can make a Tandy joke.
So now we have an R value reference, and we try to add another and to it. What do you think we're going to get here?
L value. L value.
You spot on. Did you just look that up?
No, it's look at the first one.
Oh, okay.
No.
Yeah, that's exactly what will happen. And the only case in which these will collapse to an R value reference is when we do this all the way. So these are the reference collapsing rules. They are precisely this way in order to make this perfect forwarding work.
So as a takeaway, you can compress at least 3 ends.
Yeah. Well, no, if you try writing 3, if you try to write T and, it will say no. Okay, but if you try and form these types via type defs or via explicit instantiations of templates, it's going to apply the collapsing rules. If you try and write it directly in source code, it's not going to work, but you can try and do it via a type def or so, an alias definition. So now we have the same as before, except this time I is a constant. We call foo with CI. That's going to work. And in this case, T is deduced as const int ref. Reference to constant, L value reference to constant. And by these collapsing rules, we have L value reference and, which by the second one gives us that little t has the type constant L value reference. Now we give it an R value. And now the interesting stuff happens. Because we're giving it an R value, the deduction rules change. And this time T is deduced as plain int, no reference. T is not deduced as a reference. Big T this is. So little t this time is deduced as int and, which is exactly what we want, R value reference. And the same thing, if I'd passed it, I could in some way have come up with a way of getting it to do a const R value reference, but they're not very useful. Never mind. So, standard forward. Why all this? Why all this complicated deduction stuff? Within a function body, arguments are L values. But if we want to write a perfectly forwarding wrapper, we need to know the original value category of the thing that was given to us. Yeah? Because if somebody passes us a temporary, we just want to move that temporary onwards. But if someone passes us a reference to something that exists, we don't want to blindly move that on because we could be messing with the internals of someone else's type. Right? So we want to conditionally move. We want to be able to say, if someone gave me an R value, I'll move, otherwise I'll copy or I'll pass on an L value reference. And that's precisely what standard forward does. So standard forward where T here, so you have to supply have to supply the template argument when you call standard forward. When you pass it the deduced type of a forwarding reference, it will recreate the value category that it came in as. Well, not quite, because it's going to give you an X value, not a PR value, but whatever. So standard forward is used in generic code when you want to perfectly efficiently. Oh wow, this has come out tiny. Sorry guys, you have to squint at the back. So this time we have two functions foo. One takes an L value reference, one takes an R value reference. And we have this wrapper function called non-forwarding. And all it does, it takes a T and takes a T ref ref. So this is a forwarding reference, but it doesn't actually forward. It just calls foo of T. And then we have the second wrapper function, which does use standard forward. Oh, I was going to ask you what he did, but I foolishly put it in a comment.
Well, you can't see it, so.
You can't see? Well, unfortunately, I can't move the TV much further forward than that. I'll just... Memory for next time is don't try to put too much on one slide.
Yeah.
Or to the server, please.
Yeah. So what happens here is we've got this L value I, we call non-forwarding with I, which means that which means that this value T gets deduced as L value reference to int. We call foo of T, and it calls this overload. So that's fine. It's exactly what we wanted. Brilliant. So now we call non-forwarding. So we call this function again, this time with an R value. And what's going to happen this time is T is going to be deduced as an R value reference. Okay? So when that happens, we know we were given an R value to start with. So now we call foo. Well, now T has a name in here. So T, its type is R value reference to int, but its value category is L value. So when we call this, it's going to go for the first overload, which is valid to call due to these collapsing rules. So it's going to call this L value version, which is bad. So what standard forward does is if we say standard forward and we give it the deduced type, then it will restore the original value category. So in this case, we've just passed I directly, so we're giving it an L value. Little t is deduced as L value reference to int. Standard forward does nothing, doesn't do any conversions for us, just gives us an L value reference back. We call foo with this L value reference, it's going to call that one, which is exactly what we wanted, because we passed it an L value, so we want L value foo to be called. The magic happens with this one, so when we pass our forwarding function an R value, in this case, little t is going to be deduced as R value reference, and then by the magic of standard forward, it's going to move, because we're calling standard forward with an R value reference, so it's going to move, do the equivalent of standard move for us. And when it does that, this turns little t into an X value, which is an R value, so it's going to prefer this second overload. So that's exactly what we wanted, because we gave it an R value in here, and we're ending up calling the R value overload. This is perfect forwarding. So this one is imperfect forwarding, because we're not getting the right value category. We're passing an L value in there and getting the L value version. We're passing an L value in there, an R value in there and getting the L value version. That's imperfect. That's imperfect forwarding. Perfect forwarding is the second one down there. We pass in an L value, we call the L value, pass in an R value, we get the R value overload. We have perfectly forwarded the parameter we gave it, and that's the purpose of standard forward. So you can think of standard forward as a conditional move. It conditionally turns something into an X value if it was an R value when it came into the function. Right, that I really had to rush through that because we are almost out of time. These are the takeaways. Let's just boil it down to, what's that, 6 bullet points. Always declare move operations if you define a copy. We've talked about that. Use standard move to move an object unconditionally. Use standard forward to conditionally move an object. That's a forwarding reference. Okay. Be very careful with move from objects. They're in what's called a valid but undefined state. So something that is what's called trivially movable, so something like an int, that'll be fine to use because in that case a move is just a copy. So an int would be safe, but something like a string would not be. And the standard, the documentation on CPP reference, it tells you in great detail exactly what you can do with an object that's in a move from state. But in general, the general rule is that the only things that are safe to do are either destroy it or reinitialize it by assigning to it. The last two, I only touched on the first one, I didn't mention the second one, but you usually don't need to call standard move in a return statement. So you rarely want to do return standard move A, where A is a local variable. You might think that's a good idea. You might think, oh, I want to use move semantics. Return has some magic whereby if you call return and then the name of a local variable, it will automatically do the move. And even better is that in C++17 and in C++17 it's mandatory, but pretty much every compiler since the Stone Age has optimized that, even in C++98, so that it doesn't even do the move. It just, it's called something called Constructor Elision, and it won't do that at all. So it'll optimize that out for you. But if you do standard move, then it actually inhibits this optimization. So again, Clang has a really nice warning called something, I think it's pessimizing move, which will tell you off if you try and move something in a return statement unnecessarily. Finally, this thing, auto-ref-ref. So auto uses the template type deduction rules. And that means it uses these complicated forwarding rules. So when you see auto and, it's the same as t and in a function template. And that means that this can deduce, depending on what the thing on the other side, it can either be an R value reference or it can be an L value reference. So auto and is not automatically an R value reference to something. Auto and uses template type deduction rules, so it can come out as an L value reference. Now, having said that, it is occasionally useful. I see it primarily in for loops. If you genuinely don't know the value category of something, I would recommend against using auto-ref-ref if for no other reason than it's going to confuse anyone looking at your code who hasn't sat through 2.5 hours of me yakking. And thank you very much for listening to me. I apologise if I've sent you all to sleep. I really did intend to give you more typing and less typing for me, but
hopefully I won't ask this question again.
Yeah. Well, it's hopefully it's going to be a good few weeks before I have to do this again, and I'll be there. I'll have finished my preparation that time. Yes, thank you for coming. 2 minutes to go, so yeah. Do you want to wrap up?
Thanks very much, Christian.
Oh, sorry. Yes, questions.
From last week, the CMake exercises, do we get solutions for them?
I already pushed it, so
brilliant, thank you.
Last question from me. This
Yeah.
kind of knowledge, how would you rank it, like beginner, intern, junior, mid, senior?
This is
Our
pretty.
order.
This is
Our
pretty.
order.
So
Newborn.
using move semantics, just knowing when to move, knowing how to write a move constructor, that would be intermediate. Knowing all the X value stuff,
Okay.
using all the X value stuff, all the value categories, using forwarding references correctly, that's probably getting to a more advanced level then. Ollie probably knows better than me.
I mean, I would put it definitely at a sort of senior level, at least to have a good handle on the concept of move semantics, maybe a little bit higher. I'd probably say like.
Okay.
Did we put it in the advanced? Did we put it in the advanced course when we were redesigning everything?
Yeah, we did.
There we are.
So thanks very much, Tristan. Really appreciate it.
That's nice. If anyone wants to come to the pub, I really need a beer.
Yes, so now we're going to pub. You're very welcome to join us. For those who want to join us, there is a lunch always end of the week. So you're very welcome to come in. If you need any details, email me or contact me, Christian or Ollie, and we'll give you the details. Usually it's Thursday, Friday. Yes. So thanks very much.
Cheers, guys. Are we here now for a while? I thought there was one more week we couldn't.
There is 1 week, but it's a little bit further down
Okay.
the line. So. I mean, it's going to be the date.
Okay.
Like,
Oh, okay. Then I'll get it sorted. Don't worry about it. No problem. Oh, my battery. I've killed my complaining load of shit.
Sorry, what?
Killed my battery complaining load of shit.
Did anybody sit through all that online, John? Did anybody sit through all that?
Yeah.
Yeah?
It wasn't meant, but the subject was passed.
Yeah, I know.
Being caught out of
Did you not bring a charger? Did you not bring a charger?
That's not a problem though, like,
Tristan, there are two types of people. One, who always got connected to the charger, and second, who never do.
Well, I used to be in that group, and then my laptop battery started playing up, and now I'm.
It's usually fine, except when I suddenly decide I fancy pilots and shit. It's very warm right now.
Personal project or
But the thing is, you will not freeze during the transit to the beer schenker.
Is that dual core?
It's fine.
Yeah.
It's warm there.
Quad core hyper-threaded.
Yeah, probably is, isn't it? 2+2. 9740 is an HQ.
Your emulator CPU.
VMware passed it through.